Okay, so here are the conic sections and maybe some uses. Okay, these are super, super useful. You end up using these all the time. So the first of these is a circle. How is this circle characterized?
One focal point.
Okay, there's one focal point, which we normally call the center. And this is just the things where the distance to center is constant. Cool? So that looks like this, right? There's a center, and then there's a radius. Okay, do not confuse this with the idea that the distance from edge to edge through the center is constant. That's constant diameter, which it turns out is slightly different. Cool. So constant radius and constant diameter are slightly different. We're talking constant radius here. Okay. What do you use circles for? Everything. Good answer. All the things. Okay. Let's see. Ellipse. Oh, I guess I should give you an equation. These look like x squared plus y squared is r squared, right? Okay, an ellipse looks like this. Yeah, it's like an oval. Is it an oval or is it? I don't know what an oval is. I've never heard a mathematical definition of an oval. I would assume an oval is probably not quite an ellipse. My best guess is that an oval is a circle that's undergone a linear compression in one direction or the other, and that I think is slightly different than an ellipse. But don't quote me on that; I could be totally wrong. I'm going to actually have to sit down and now think about, yeah. I'll go look. An ellipse has two foci. Careful with the guns; they're stabby. So the way you characterize a point on an ellipse is that the sum of the distances to the foci is constant. You guys see that? So sum of distance to foci is constant. And it turns out that if you write down an equation for this, you get an x over a squared plus y over b squared is 1. Cool? You guys good with this? Okay, uses of these?
Orbit around.
Yeah, so it should be noted that normally you would think about circles as orbits in space as circles. But it turns out that with probability 1, they're ellipses. Yeah, meaning if you pull a random rock out of the universe that's orbiting something, it's orbiting that something in an ellipse, not in a circle. It's not physically impossible for it to be a circle, it's just really unlikely.
Have you seen that video too where it shows the sun moving and it shows the planets trying to catch up to it, so it's all kind of a vortex?
Mm-hmm. Yeah, those are cool. You can make one.
Oh yeah.
Yeah, you can make one out of a big sheet of stretchy nylon and ball bearings. Super cool. Highly recommend this experiment.
Most people think of it as stationary, but of course it's all moving.
Yeah, but of course everything's moving.
Yeah, it's crazy.
Okay, so that's an ellipse. Use them for orbits. There's also a kind of a cool thing that you can make what's called a whisper chamber.
I know those.
Which is you can make an oval or an ellipse-shaped room, and if you stand at one of the foci, you can be heard perfectly at the other foci,
Because all the sound.
but nowhere else in the middle of the room.
All the sound.
Yeah, the chairs on opposite sides of the room.
Yeah. So you can make this room where if you sit here, and your buddy sits there and lots of people stand around, you can talk at a very low tone, and they'll be able to hear you perfectly, but no one else in the room will be able to make it out. Yeah, there's a legend about Thomas Jefferson, so probably bullshit. Okay, so circle, ellipse. Where's Nicolas Cage when you need him? I know. Okay, so a parabola, you guys know the equations for parabolas, right?
Yeah, sure, where?
They look like y is x squared plus some constant, right? Okay, cool. All right. Parabolas are good for the following. They look like this. There's a dot and a line. And they're the distance from focus equals distance from line. Oops, from line. There's a special name for that line. Oh, good, it's called a directrix. Sure. Cool. All right, what is the use of a parabola? Yeah, any kind of satellite dish or signal gathering device follows a parabola. There's also the mirror on the hotel in Vegas, which was a bad idea, it turned out. Did I tell you guys about this?
Yeah, deaf pool.
Yeah, the deaf pool. So they built a building, right?
Oh, and then the pull up on the top.
Building, and then they indented a parabola into the building's face
Okay.
in such a way that the focus was at the pool.
Oh, sunlight does something.
But of course, yeah, this is a bad idea because the sunlight bounces off this thing and it focuses it right on that. So it bakes you if you sit next to the pool.
Yes. Oh, you want
Okay.
to get a super tan, go there.
Yeah, so they actually had to go in and just kind of alter the geometry of all the mirrors in there to make sure that it didn't cook people. I mean, it wasn't like 1,000,000 degrees. Like, this is not starting bath towels on fire, but it is enough to give you a hella bad sunburn in a couple of minutes. So, yeah, careful with parabolas.
It's the cheapest way to heat the pool, right?
It is definitely a cheap way to heat the pool. That's true. It gets less cheap when you factor in the lawsuits, but also it's Vegas, so you really only need to heat the pool half the year anyway. All right, so that's parabolas, and the other one is hyperbolas. Which I probably have spelled wrong. So a hyperbola has the equation x over a squared minus y over b squared is 1, or is constant. What? What? That's
Is it like,
what's weird.
One time in the left.
Yeah, it's like an ellipse, right? But it's a minus instead of a plus. You guys see that?
so instead you get it like this, or this?
Yeah, so depending on which one you're subtracting, I guess I should write minus plus and plus minus. Meaning that the signs on these are opposite, right? But it doesn't particularly matter which one's which. It will give you the difference between this kind of thing and this kind of thing. You guys see that? Like these are, why am I doing this with one color? I have another
I
color.
figured it's kind of like the ellipse where it's, you're taking apart the circle and going
Maybe
I don't know, the subtraction part comes into play with that, right?
Yeah, so the way this is characterized in distance land is instead of the sum of the distances to the foci is constant, we're doing the difference of the distances to the foci is constant. You guys see that? And the foci sit over in here somewhere. Okay, so what's this thing good for? Yeah, actually, hilariously. Approaching objects you don't want to hit. And if by hit, you kind of mean hit or end up in orbit around. So this is how you do a gravity slingshot. So when we send a probe to Mars or when we send a probe to Jupiter or something, it's often a good idea to get a gravity assist from the sun. And the way we do that is we kind of pop the satellite at the sun, but intending to miss a little bit. And then it swings around the back, and because the sun is moving, it ends up getting a big boost in momentum. You guys see that? So you can use this to kind of garner some speed. Cool. These are also how it works when an asteroid has a near miss with a planet, right? It comes in, but it's not going to achieve orbit, so it just kind of gets bent by the gravity well. You guys see that? This is also what it looks like when you screw up a lander. Like the Mars lander that we screwed up a few years ago because we forgot to convert from meters to yards.
Oh.
That was one like this. It went and was going to insert, and they were off by a little bit, and so their velocities were wrong, and so it didn't insert. It just kind of banked off the side, which is really what's going on here. You really get one of these, right? You guys all see that? That path will follow one of these things. Cool? Questions, Steele?
You get one of these, right?
Only one of these will appear, right? Because you really only have one object you're trying to slingshot around. So you're not going to see both of these because there's kind of two paths you could be on, and you're not on that one.
Becoming a shallow enough an angle to, or a shallow enough.
Yeah, you're really kind of thinking. Like, here's your object, right? And you could really think about this thing as sitting in kind of a cloth bag. You guys know this for thinking about how gravity wells work?
Yes.
So this thing kind of dents space-time by sitting there and having mass. And so orbit, right, is when an object is kind of slinging around that hole, right? And it's got to be going pretty fast to stay in there. If it goes too slow, it'll fall down to the bottom, right? It'll end up on the planet or whatever. If it's going too fast to end up in there, you'll see it kind of come in from the outside, and it'll sling around this thing and go back out the other side. If you look at that in a two-dimensional way, you're going to see a hyperbola. Yeah, so wormholes are sort of the idea that two of these things might like go down and connect, which is not really ruled out by the math, but the physics is a little funny.
And the gravity well is just.
Yeah, it would be an infinite gravity well of kind of arbitrary depth and do something kind of weird at the bottom. Don't get attached to this, it's just a metaphor, which is kind of the problem we have with wormholes. Like, they're a metaphor. You try to treat it too literally, weird shit happens. Cool? Questions, Steele? All right. So that's what I want from you guys for Conic sections. If you could at least recognize the idea of some of these, like the two outcomes I really want are for you to be able to look at the graph and say, that's a circle, that's an ellipse, that's a parabola, that's a hyperbola, and for you to look at the equations and be able to do the same. That's basically it. Yeah. This is one of those things that you use often enough that I expect that you probably have some facility with it. But I also don't expect you to be working out orbital mechanics unless you're really into Kerbal Space Program. If you're super into KSP, though, you'll want to sit down and work these.